My name is Jeffrey Sachs. I'm with Extreme Optimization. We make numerical libraries for the .NET platform. Last year, I gave a talk about numerical computing with the CLR. This year, I'll be talking about the DLR. Before I get to that specifically, I want to make two small excursions. One is I want to go over a few things that have happened in the past year in the numerical computing space. 5 significant things have happened. We're going to see some new types in the CLR 4.0, and like complex and big integer and stuff. And I'm sure we'll learn more about that tomorrow. Parallel Extensions has, the group has announced that they are going to interoperate with existing parallel standards like OpenMP, which is a big deal for numerical computing because so much code is parallel already with those other standards. Third is that Mono has published extensions for SIMD instructions, single instruction, multiple data, which should speed up some calculations. Fourth is IronPython has finally gotten NumPy support through the work of Resolver Systems, who have developed Ironclad, which is an interface between IronPython and CPython extensions. And finally, we have F# coming up, which has also added units of measure. The second thing is an issue with .NET libraries and the expansion of the .NET platform to dynamic languages. The CLR is, at its core, an object-oriented runtime. And the initial languages, C#, VB, and C++, are really made to fit on that object-oriented platform. With the new languages, they have their own patterns and practices, their own ways of doing things. And as a result, what you see is that you get these, for example, Python using Python libraries and Iron Ruby using Ruby libraries, and you get less of these languages using good old .NET libraries that have been developed over the last 5 years or so. So in other words, writing .NET libraries that are universal for the entire CLR, not just the object-oriented part, could be made a little bit easier. One thing we need is design guidelines. How do you write something that is easily callable from Python in the way that Python developers are used to writing it? Same thing for F#, same thing for Iron Ruby. Second thing we need is some standard way to implement language bindings. For example, in F#, there are certain language features that require type augmentations. You have to write a little snippet of F# code that adds a method to a type in your library to make it work with F# properly. So it's more than just the naming issues that Ruby had. It's more like, how do I use this? F# commonly passes functions around. That's not really the style that C# and VB developers are used to. So how those interfaces should be easy to write as well, and to in some way be easy to ship with a product without requiring references to the F# assemblies. So anyway, those are two asides. Back to numerical computing, and there's 3 things I want to do today. One is discuss how expression trees can be useful also in static languages. I'm here talking not about dynamic expression trees or dynamic dispatch, which we just heard about. I'm talking about just pure static expression trees, which are also part of the DLR. Secondly, I want to talk a little bit about numerical languages, dynamic languages that already exist for numerical computing, and then introduce M#, which is a language we wrote on the DLR, which is array-based and I'll give a brief demo of that and show some benchmarks. So, expression trees in static languages. There's 4 things that I see could be done with that would be useful. These are things that aren't necessarily possible today, but they might be possible tomorrow. One is compiler extensions. What I mean by that is that the compiler at compile time passes an expression tree to an extension, and the extension can rewrite the expression tree and pass it back to the compiler. One example of this today is how C# and VB rewrite compound assignment operators. One way this is useful is, anyone remember how big integers was pulled from the .NET 3.5, I think? One of the reasons was that certain operations were very inefficient. It created lots of temporaries and so on and so forth. And with this kind of extension, you could pass an expression tree of operations on big integers off to the extension, which rewrites it in an efficient way and gives it back, and you don't have the kind of issues that you have today. So that's optimization, but also simplifying syntax. You can do a lot of the same things today by writing methods, add methods, and so on and so forth, instance methods, and so on. It's a little bit complicated for users to remember all that. It doesn't look nice. It doesn't look mathematical. So once again, if you can rewrite those things, or have the face of it be nice and tidy, and then underneath by the extension have it rewritten, that's a great plus. And one final possibility there is to implement mini DSLs inside a language. Another application of expression trees is when you need to manipulate expressions at runtime. Once again, this is static expression trees. An example of this is in an arbitrary precision context. Say you want to calculate the tangent of pi to the power 100 to 20 digits after the decimal digit. You do that in 3 steps. You compute pi to a certain precision, raise that to the power 100, and compute the tangent. Now, if in this calculation C is very large, then probably the precision you used to calculate B wasn't enough, and so precision you used to calculate A wasn't enough. So what you need to do is you need to go back and re-evaluate the same expression with a better precision. And the only way to really do that is if you have the expression tree available at runtime. That's another example of what you can do with expression trees. Third, model specification. This came up in compiler extensions as well. It's really the same thing, but at a different point. The reason I got this idea was from looking at Microsoft Solver Foundation, which is a great product. They have their own kind of modeling system where you can write constraints and so on concisely. Unfortunately, because they couldn't use expression trees, they had to write their own set of expression trees. They couldn't use the link expression trees, is what I mean. So they had to use their own system. If you had unbound expressions in the available, like right now the only way to have an expression is as part of a lambda expression. You can't do, for example, 5 times a parameter expression of type integer and assign that to a variable. Even though at compile time you do know that the expression is valid. So you know the type of the expression is completely specified and known at runtime. Oh, at compile time, sorry. So if you can have that, if you can have those unbound expressions, then you can write out models more easily and effectively and once again, it opens up a whole world. The last thing that you can do is obviously symbolic computations. Applications are too many to mention. With the new DLR, you can use, or the new style expression trees, you can use reducible nodes so that you can interoperate without many problems. And a lot can already be done with the expression trees that were part of .NET 3.5. In fact, the next version of our libraries will have symbolic derivatives of lambda expressions and stuff like that. Okay, back to dynamic languages. When you look at the numerical computing marketplace, or the kind of products that are available, pretty much every language that is used for technical computing is dynamic. There's MATLAB and its variants, there's Mathematica, there's R for statistics, and also Python with NumPy. Sage is a system built on Python and NumPy that is pretty extensive, and that's also supported by Microsoft Research. On the .NET side, last year I talked about the things that could be improved in C# MVB. F# is a fantastic language, but it scares a lot of people because it looks funny and like it's basically a fear of the unknown. Iron Python also works, especially now that we have NumPy support. So we're doing not too bad there. The challenges are that, talking specifically about Python now and NumPy, if you have to dispatch to other external interfaces, COM interfaces, and so on and so forth, your deployment scenarios become complicated. You can't always run it in protected contexts or Silverlight or in SQL Server. Interop can also be slow because there's an overhead with the dispatch continuously. So it's okay if you run big chunks of calculations, but if you have a lot of fine-grained calculations, the dispatch gets to dominate and performance goes down tremendously. The last challenge, which in my experience is extremely important, is how do you bring the people who use these systems, who use these dynamical languages to build their models, how do you bring those people into the whole development experience? A lot of times I hear programmers tell me, okay, my statistician gave me this R program, or my financial analyst gave me this MATLAB program, and what do I do now? So that's probably the biggest issue that I can see, or the biggest killer of productivity that I can see in this space. So, for all these reasons and more, we built M#. M# is a language that uses arrays as its basic type, and one of our objectives was to bring in those people that are comfortable with array-based languages. Why is a dynamic language appropriate? Because the process of model building is extremely interactive, and so they definitely need that kind of environment. And also, engineers, scientists, they just want to get the job done. They don't care about syntax too much. They don't care about types, if they know what that is. They just want to get the job done. So why yet another .NET language? Well, initially 5 years ago, I wrote a first version as a sample for our libraries. But there were problems with that, especially user interface problems, and that's not our strong point, so we kind of abandoned it. But it got revitalized with the coming of the DLR, and now it sort of got out of hand a bit. what we want to do is build a 100% managed array-based language. Benefits I've talked about before. Deployment is easier. You can run it within SQL Server or Silverlight. And also, you don't get the overhead costs of comment drop and other types of interfaces to external libraries. Thirdly, it's not really yet another language. It's in the spirit of MATLAB and Octave and those kinds of things. So it's been around for 20, 30 years. And millions of people use it in their work daily. Millions learn it in college. And so a whole lot of people are already familiar with the language itself. And thirdly, we built it because we can and because the DLR really makes it easy to implement a language like that. Specifically, easy are generic computations, so computations with any data type, symbolic computations. The DLR uses expression trees, so you already have the expression trees built. So you don't have to do all that part separately. And then functional style programming is also easy. You just pass objects around and the binding takes care of invoking functions and so on and so forth. So what did we find difficult? Mostly the DLR is still very much a moving target. It's under heavy development, changes a lot, and it's sometimes hard to keep track of what's happening and what will work now. And when you look at the source code, there's a lot of this will change or we have to revisit this, and it's generally the typical things you expect from a work in progress. Specifically, we found difficult trying to get runtime optimizations going, because what usually happens is the dynamic binding actually usually combines the actual binding step with the evaluation step. So if you have an expression tree that you want to optimize, you only see the top level because everything below that has been already evaluated. There are ways around that, but as I said, it's kind of hard to get everything going with the state of things today. Something else that could be slightly improved is static binding. There's no reason why, if you have all the information available, why you can't actually use static types wherever you can, especially in a numerical context where Python and Ruby make everything dynamic, and generally the overhead of tests and so on and so forth, runtime tests, is small. But if you have a function that is executed in an inner loop, then those extra instructions cost a lot and bring your performance down. And third, sure. Sure.
I'm very puzzled by that issue.
What do you mean?
The DLR trees let you do static binding when you want to?
Yes, it does. There's just this is a small point. There's a few ways it could be made easier. It's not very important. Thirdly, overload resolution. There's a few things missing there. Resolving generic methods is not supported, and also certain things like, one thing we want to do is, if you have a function like assign or something, if you have that defined for a double, we want to also use that for, or make it available for an array of doubles automatically. But right now you can do it, but it's a whole lot of work to actually make it work, so that could also be improved. So let's do some actual coding. Show the kinds of things we can do. As I said, it's an array-based language, so we can do things like create ranges with slices, and do computations with that. Let's create a random matrix. And then we can do things like compute the row sums or column sums, so on. We can do indexing with range indices. Come on. And one useful thing is also you can do, you can use tests in your or Boolean expressions as an index. Oops, what did I do? There we go. This gives you a list of all the numbers that are greater than a half in your matrix. You can also just use the, CD. Come on. See the values in the original matrix that are greater than a half. And you can do assignments that way too. So all those values have been updated now. You can have multiple return values. You can do computations like determinants. Oops. And also, as I said, it's easy to do operations, generic computations. For example, if we create a matrix with rational numbers, then we can sorry about this. There we go. And let's just give that a value. This is a matrix and the elements are rational numbers. We can compute the inverse of that matrix. And you can see that it's actually the inverse because if we multiply to make it, one's on the diagonal. We can also do computations with arbitrary precision numbers. So we can compute pi to 50 digits. Or pi to what? Let's do 100,000. And that'll take a few seconds, but it'll do it. We can do convert to big arbitrary precision numbers and then do calculations on that. We can work with functions very easily. For example, Newton's method to compute the roots of an equation is very easy to implement. This is how you would write it. And then if we use two functions, one for the cosine and one for its derivative, then we can write something like, Newton, and then the @ sign is a function handle. The reason we have that is because we can have optional parameters, and if all the parameters are missing, then the function is called without parameters. So to distinguish a function call from the function object, we have to add the @ sign. So if you look for the solution, we find that pi over 2 is a solution. We can also do that with arbitrary precision numbers. And this looks rather big. yeah, what happened here was, yeah, the operation. Oh, actually, it's still a solution because, oh, come on. I gave it a starting value of pi and the cosine of phi. The derivative is 0, so you get an infinite or close to infinite division. But if we actually look at the result, see, it's pretty much 0. So we're still correct. So if we start from another value, we can have something different, and then we'll find that the answer is indeed pi over 2. And then another thing I talked about was symbolic computing is easy. Well, this is actually quite fun because the DLR is all about expressions and expression trees, and symbolic computing is about expressions and expression trees. So you're basically manipulating expression trees using expression trees, which is a lot of fun. So let's create a symbol. And let's do another one. Y. This is really just a parameter expression. If I do class X, it says it's an expression. Then I can do things like write a matrix that's made up of expressions, and I can see that and I can do things like compute the determinant of this matrix. Oops. And it's not very clean, but if you actually do the calculations and simplifications, then you find out that it's actually the right answer. So this is just pretty basic stuff. We've not implemented the whole simplifications and so on. It's more of a proof of concept that you can do those things very easily. Yeah?
So APL had the concept of essentially saving and restoring your workspace. Do you have,
Yes.
have you done that same?
That will be available. It's not done yet, but yes, that's definitely part of what we'll do. And then one last thing I want to show you before I go to the benchmark results is to show some graphics. No demo is complete without some graphics. So here's a range of values, and let's see, we plot that and the sign. And we get a nice plot. And we can add cosine to it. And we have a graph with sine and cosine there. So that's a very, very quick overview of what you can do with M-sharp. One thing that surprised me was the performance, which is actually excellent. We ran a series of benchmarks. There's one that was published on the web that compares a whole lot of different environments like MATLAB and R and Octave and all of those. So I took that one as an example and ran some tests. And the results were pretty good, I'd say. The blue bar, the first bar, is M-sharp. The red bar is MATLAB, an older version. Green is Octave, the open source MATLAB clone, and purple is R, the statistics package. And I'll just go to the actual summary.
The units on the x-axis.
The x-axis are different benchmarks. For example, the first one here is does transposing, which .NET, it's basically moving data around, and loops, which can't always be optimized. So .NET is always a bit slower in those things. But for things like, for example, the last two are matrix multiplication and division, which work really well. and here, matrix functions is things like determinants and decompositions and Fourier transforms and stuff. Programming tasks are more the small grain stuff, like more programming than, or more running an actual program rather than a specific calculation. And statistics is some applications for, or specifically for statistical computing, like getting a million random numbers and stuff like that. So this chart adds up all the times. It's not exactly scientific, but it does give you a good impression of what we have. We didn't do too much optimization, and yet actually hardly any at all. And yet we are already at par with a commercial product, MATLAB, and we're faster, significantly faster than 2 open source projects, which is in large part due to the great work of the DLR team. So I was personally really impressed with the performance. Pardon? 7.0. Yeah, they've just introduced a new version that has that lets you call .NET objects. So that was just last month, by the way. So you can now call .NET applications from .NET from MATLAB. Yeah. So where are we going with this? Well, as I said, one of my important points is that we want to bring in those scientists and those engineers and those statisticians and those mathematicians into the development community, integrate them into the whole development process. So you have to give them an IDE then. And what do they need? They need a rich interactive session, like with a read, evaluate, print loop, which we're getting with F# and with the dynamic languages. We need code editors and for scripts and functions. We need tool windows for things like graphs and charts and data editors. The statisticians will definitely need good database connectivity. And we have to make it easy to transfer between different, from prototype to actual application. Now, if you look at these features, some of you might see some resemblance with certain products that we are very familiar with. And that's really where we're going as well with this. The goal is to have a Visual Studio-based environment for technical computing. So, conclusions are that the DLR is a fantastic product. There is some danger in losing out some of the traditional object-oriented .NET libraries that may lose out to Python or Ruby solutions. But overall, nearly all the building blocks are in place to make .NET a really great platform for numerical computing. So, question time.